Hello everybody, and welcome to the exercise on page 55 of the workbook. This is going to be an example of estimating a double integral of a function. Okay, so let's read this question together. So we've got a 4 meter by 3 meter metal plate of varying density. It's given by a function f of xy grams per square meter. Okay, and we've got a contour diagram for the function shown over here to the right. And they'd like us to chop this plate into pieces of size 2 by 1 and use that to estimate and interpret the value of the integral. Okay, so before we dive into the problem, let's just kind of take stock of what we have here. So first of all, notice that the density of the plate at various points is being given by these numbers. That's kind of the meaning of a contour plot. And they're asking us to chop this essentially into 6 little subrectangles. Delta x and delta y, if we sort of draw them into our picture, would be here. Delta x is 2, and here. Delta y is 1. Okay, so what we're going to do to estimate this integral is something that I like to call a middle sum strategy. Okay, you might remember hearing that term in Calculus 1 and Calculus 2. The idea here is going to be very similar. Okay, so this integral that we're about to calculate, okay, integral over r of f of xy times dA. Let's remind ourselves of what we're really doing when we integrate a function. It's about taking values of our function and multiplying them by areas. Okay, so what we're going to do is to take our metal plate, chop it up into pieces, and then multiply values of the function times the area of our pieces. The idea of the middle sum means that we're going to take our function values at the middle point. Okay, so how does all of that work? Well, we'll start by just grabbing one of the subrectangles, okay, the one in the lower left-hand corner, and I'm going to do my best to draw the middle point of that rectangle. What would you estimate the density of the rectangle to be at that center point? Well, notice that that point is between the 300 and the 400 contour, so I'm just going to take 350 as my best estimate of what the density is right at that point. Okay, so we've taken the function value, and now we want to multiply by the area of that rectangle. The area is just going to be delta x times delta y, which is 2 times 1. Okay, and there's the first term in the integral that we're estimating. Okay, next, pick another rectangle. Okay, I'm just going to jump to the right, find its center point. That would be about here. Okay, and do your best to estimate what the density would be at that point. Okay, that's between 400 and 500. Looks to be a little closer to 500, so I'm going to take 470 as my estimate. Okay, and this is not an exact science. You may come up with a slightly different estimate of the population, not population, just the ordinary density. And that's totally okay. And we just keep doing this until we run out of rectangles. So if we jump up here and find the center point, okay, the population density there is between 200 and 300. I'm going to take 240 as my estimate. Okay, multiplied by the area. Okay, then next we're here. Okay, and the center point looks like our population density is maybe around 350. Okay, times its area. You notice that the area of all of these, every one of these subsquares is 2. Okay, and there the center point population density is maybe about 140. Okay, and then finally the last one, if we look at the middle of the last square, okay, that's here, that's really close to 300, so I'm going to take 290 as my estimate of the density. Okay, and you might have heard me say population density a couple of times. I've kind of got the last question in my head. I should not be saying population because we're just talking about ordinary weight density here. Okay, so I apologize if I said population. Okay, well, what do we get if we add up all of these numbers? Okay, well, notice that this 2 times 1 appears in every single term. Okay, so we can factor that 2 out. You might remember that we used that same strategy in the example on the previous page. So we're going to get 2 times the sum of all of our densities. Okay, let's make sure that we copied all of those down, right? Okay, looks good. And if you do the arithmetic here and multiply those together, you're going to get 3,680. Okay, now the question is, what is the meaning of that number? What did we just measure there? Okay, well, we can answer that question by thinking about units. Let's go back up to the integral at the top here and just ask what are the units of each of the pieces. So f of xy, that was our density function. You can look back in the problem and notice that that was measured in grams per cubic meter. Okay, and we multiplied that f of xy by an area. An area, in this case, was being measured in meters squared. Okay, we're multiplying those, so what happens if you multiply those two units? Well, the meters squared goes away, and we wind up with units of grams. Okay, so ask yourself then, what kind of a physical quantity gets measured in grams? Well, grams is a unit of mass, and so we could say that this integral represents the mass of the metal plate. Mass of the metal plate in grams.